Welcome to EfficientML.ai lecture 9. So today we are going to talk about knowledge distillation. So first, lab 3 is out, which is about neural architecture search. We carefully designed the Google Colab, provided you with the once-for-all network, which is already pre-trained, so that you can search an efficient architecture by sampling different subnet networks from this once-for-all network. Very affordable search cost. You are going to implement the evolutionary search with different constraints to find the model with the best quality, which is pretty fun. And also, in order to improve the quality of our TA's question answering, we created Piazza to help you answer the questions for the registered students. Students who are officially registered in this class. Since we don't have the bandwidth to reply, we get overbooked unexpectedly. Large number of audiences, that's very good, certainly welcome. But we only have one teacher and 2 TAs, limited capacity, so we want to make sure we answer your questions very timely, very carefully. So we have this Piazza group for registered students. And some of you also mentioned it's helpful for doing the group project, since we want to find the teammates who are also students who are officially registered for this class, smaller community. So make sure to ask the questions related to the lab, to the project in Piazza. Okay, so before jumping into today's lecture, I'm going to show something fun. So we've been working on a project called streaming LLM. So streaming large language models with attention sinks for you to continuously chat with a chatbot with non-stop chat. We're going to cover about the details in the large language model part of the lecture, but here we want to show you a demo. So this previously, without streaming LLM, model performance first break after reaching the window size and then out of memory due to the limited size of the memory for the KB cache. But after applying streaming LLM, you can continue to chat, answer questions, chat with the chatbot. An interesting finding actually dates back to 3 years ago when we worked on this paper on Saturn, efficient sparse attention for with cascade token head pruning, and we observed a very interesting phenomena. We at that time didn't get an idea how to solve it. Like the first token is super heavily attended to, no matter what token it is. So like here, he's a very famous researcher in the computer architecture area and has published many independent papers. But why are papers so heavily attended to the first character? And similarly, for this sentence here, we can prune a lot of tokens, but the first one, we have to keep it. Like Du Fu is just a person's name, but why Du is important, Fu is not? Doesn't make sense, right? And 3 years later, we finally find the idea. This is called attention sink. We have to dump a lot of the attention scores to one of the tokens, even if it is a space nonsense token or just a /n, just change have a new line. Since the softmax function has to sum up to 1, there must be some places to dump those unnecessary weights. So the first token is important when you have to keep it. All right, we'll jump into our main lecture. Hope that gives you some idea about the latest research and some of the fun stuff you can potentially work on in the open-ended course project. So the challenge here is that we want to deploy deep neural nets even if we have limited hardware resources, not only on the cloud, but also on the edge. Even on the cloud, we want to use low power, green AI, save the power, save the planet. Right? But the computation capability difference is huge, from several hundreds of TOPS per second. This is a bit outdated. These several hundred TOPS per second versus million flops per second. from tens of gigabytes to only a few hundred kilobytes. From ResNet, VIT, to MCUNet, MobileNet to tiny. So neural network has to be small to fit these edge devices. But we know how to train large model. But how do we train tiny model? Can we get the help from this large model as a teacher? Teacher, student, large model, small model. Okay? So tiny model are hard to train. They tend to underfit on large data sets. Like ResNet 50, this is the top 5 accuracy versus the top 1 accuracy on ImageNet. Top 1 accuracy can easily reach beyond 76%. Well, for those MobileNet V2 tiny, the top 5 is only 52%. Top 1 is lower than 48%. So how can we help the training of this tiny model with the supervision of this larger model? So that's what distillation is about. So this is the illustration of knowledge distillation, where we have a teacher network, we have a student network. Given the inputs, both of them are going to get a logic. And given the logic, we can get the classification loss. That's what we normally do. And here we want to compare the logics from the teacher model and the student model. And how do we supervise that? We want to make sure the student's logics can mimic the teacher's logics to get extra supervision beyond this classification loss. So let's see example. Given this image, a cat, we pass it through a teacher network. Assume this is a 2-class classification, cat versus dog. And the larger model says the logic is 5 and 1 after the last layer. And we pass it through the softmax. And we get the probabilities. So this is the logic, this is the probability. And how was that calculated? We are pretty confident here. We have 98.2% probability this is a cat. And it's calculated by the ext5 divided by ext5 plus the ext1. And this is 5 and 1. That's basically what softmax is doing. And similarly, we have the probability for the other class, for the dog. If we see the smaller model, the prediction is less confident. The logic is 3 and 2 rather than 5 and 1. And the probability is also smoother, not as confident. Like 98%, here we are only 73%. Okay, so the student model is less confident. So what we want to do here is to boost the probability of the student to mimic that of the teacher. Okay, so here we can also apply a new concept called temperature, okay, to smooth this probability. Like here, temperature is 1, then we divide 5 and 1 by 1. Otherwise, if the temperature is 10, each term in the softmax, we divided that by the temperature. So the general principle of model distillation is try to match the prediction from the logics from the teacher versus the student model. Okay, try to match the probability given by the exponent of EZI divided by T. T is the temperature versus the sum of all the classes, where C is the number of classes. And T is the temperature, which is usually set to 1. And the goal of the distillation is to align the class probability distribution from teacher and student networks. So let's see what do we match. Okay, there are several different choices. We can match the output logics, the intermediate weights, the intermediate features, the gradients, sparsity pattern, relational information. A lot of different places we can match the teacher and also the student. first one, the simplest one, most widely used one is the logic. Okay, like using the cat and dog example, we have two classes. The last layer's output is either one is 5, one is 1. Then we directly try to match that. We can use different losses. We can use the cross entropy loss. We can also use the L2 loss, different choices to match the teacher's logic and student's logic. We can also try to match those intermediate weights, teacher's weight, student's weight. And we can try to make sure they are the same. But what is the catch here? Can we directly calculate L2 norm, L2 distance between the teacher's weight and the student's weight?
So no, because the whole point of the series is smaller models, so they're not a one-to-one network.
Right, exactly. The student network is smaller. That's all the purpose of making it smaller, right? But how can we match a larger weight tensor with a smaller weight tensor? You can add a one-by-one convolution or add a fully connected layer to project it. So here, this is a teacher network. This is a student network. Teacher is wider than the student, right? So for the student network, we can pass it through a fully connected layer to project the dimension to match the teacher's dimension. And you can learn this projector, this blue part, end to end. So other than the cross entropy distillation, we can add the L2 loss between teacher's weight and also student weight. Now, of course, the linear transformation is needed to match the dimensionalities between the teacher and the student. So that part, the blue part, is the linear transformation. For example, if the teacher's channel is 512, student's channel is 256, what is the dimension of that projector from student to teacher? It's 256 by 512, okay, to match the number of channels. That is a simple FC layer used to align the shapes of teacher and students' weight tensor. We can also match the intermediate features, not just the weight, but also the intermediate feature. Not only the last output, this is the last output feature, the last feature map, and this is the intermediate feature map. We can apply the knowledge distillation KD loss to match the intermediate feature maps. And also the gradients. Okay, we can also try to match the gradient. So here is a plot of intermediate attention maps. Okay, we are back propagating the loss to the feature map. And there are so many channels, right? We can either sum up the channel or sum up the square of the channel, right? And see where is the gradient. If this part is larger, then it means if these pixels change a little bit, it will drastically impact the output. The output will change a lot. So that's the meaning of the attention map and gradient. It indicates where is the neural network think. And this is important. Right? Thinks this part is important, which makes sense for this fox. So the intuition is that if the gradient is large, small perturbation at that pixel will significantly input the output. And then as a result, the network is putting more attention to position ij. And assume if you have a teacher model and a student model, they should have similar attention map in this case. And we try to match that part. And certainly, we can compare different model architectures. NIN, which has only 62% accuracy, network in network, versus Resident 34, Resident 101, they have much higher, 10% higher accuracy, 73, 77. Although they are different accuracy, but their attention map is similar compared with this poor network. The attention map is quite different, right? But these high-performing models, their attention map are very similar. No matter what way do you use as a reduction function, since you have to do the reduction across multiple channels. You can have 64 channels, but now you want to have only one map, then you need different methods to reduce them. You can sum different channels, sum the square, sum the to the power 4, max, sum, etc. All kinds of functions. You can try to match different reduction approaches. So this is matching the intermediate attention maps. Calculate the gradient with respect to the feature map in layer 1 and in layer 2, and try to match this part. What is the dimension of the gradient? It's the same as the weight, right? And since the weight, they might have different dimensions, the gradient also may have different dimensions. And we can use a linear projection, the FC layer, to project it to make sure you can directly calculate the output distance. Another interesting part, we can also match the sparsity pattern. So sometimes after the ReLU function, a neuron is activated if the value is greater than 0. Otherwise, it will be 0. We use this to indicate the ReLU function. So we try to match the teacher and student's sparsity pattern. If for the teacher, if this is 1, for the student, it should also be non-zero, greater than 0. Otherwise, if the teacher is 0, the student should also be 0.
So when we do this linear projection, are we effectively, we're just trying to coarse grain a large weight system? And so like each, is that correct way to think about it? So that each weight in the smaller model would just be a
Combination of
estimated sum
yes,
of them?
yes, a linear combination of the bigger model. That's what linear projection is doing.
Okay, so this is approximating multiple weights
With one or fewer weights.
Is it so important how that projection is done, or just projection you choose? There's that something you also there. Okay.
That projection is trained end to end, trained together. And sometimes there are some tricks for doing the projection. For example, you want to apply some clipping, etc. There are some tricks in the projector. Finally, we can also match the relational information. So what is relational information? So far, we just talked about try to match a single point, like first module, second module, we try to match the teacher and students module, right? But here, what it does is try to match the relationship before and after the input passed through this module. So here and here, they are from the same stage, therefore they have the same resolution. The channel might differ. This might be like 224 by 224, 64 channels. Sorry, 3 channels. And here might be 128, 112 by 64 channels, right? And here is the same for the teacher. So here we can compare the difference. So we do an inner product between here and here. I made a typo here, so it should be the same resolution. Therefore, you can assume they have different channel number, for example, but same resolution number. For example, both of them are 112 by 112, but here might be 64 channel. Here might be 256 channel. Okay, therefore, you can get a 64 by 112 a tensor by doing the inner product between the tensor here and tensor here. Let me write it here. For example, the input, you have 112 by 112 by 64. That's the input of this block. And since they're of the same stage, the resolution is the same. So this is the output of that stage. And you can cancel in the XY dimension to do a reduction in the XY dimension to matrix multiplication. So what you get is a tensor of 64 by 128. Okay. So you do the reduction since they are all the same stage, same resolution. So you can get this matrix. And similarly, for the teacher, you can also get such a matrix, and you can try to match this 64 by 128 matrix. So this is not only looking at one feature map, but you are looking at the relationship of two feature maps. Another interesting scenario is we can also try to match the relation between different samples. Like here, we have different inputs, okay? And for the teacher and student, and as P1 for teacher 1, student 1. This is for the second image, teacher 2, student 2, third image, teacher 3, student 3. Previously, we are trying to match teacher 1 with student 1, teacher 2 with student 2, try to minimize this pairwise distance. But we can define another similarity between the relationship between S1 to 3 and teacher 1 to 3. They may be just shifted a little bit, but they both form very similar relationships with each other. So this is the difference between conventional knowledge distillation and relational knowledge distillation. They try to look at the relations between intermediate features among multiple inputs. Here we can take a closer look. This is individual previous conventional knowledge distillation. I try to match the teachers and students feature map among different inputs, different examples. We have n examples here. But now we also have n feature maps for the teacher and also n examples for the student. But here we try to define the feature of all these n students to be the distance between the student, the first input and second input, and also the first and third, and also the first and the last. So we are trying to find the diff between the features of different inputs, and we use that as a feature of the teacher and also of the student. And we try to match this feature, this relational feature. So this is calculating a diff between the first input and second input and third input, and trying to match this relational difference rather than directly matching the green and the blue. Okay, so we talk about what to match. And so far, what we discussed is all about one teacher and one student. But what do we need? We only need a small student model. But in order to train a small student model, we first have to train a large model. That is obviously an overhead. Can we get rid of that overhead and just train one model? You cannot distinguish which is teacher, which is student. And do the self and online distillation. So we'll talk about self-distillation without a teacher, or you are both a teacher and a student, you just teach yourself. Online distillation, and also combining them together. And let's see how that works. Like previously, we need a large and fixed teacher model. That one is never updated. Well, we're just updating this small student model. So what is the disadvantage of this fixed and large teachers? Does it have to be the case that we need a fixed large model during knowledge distillation? Can we open the box by either making the teacher to improve or completely get rid of the teacher? That's what we are trying to solve. So I'm going to introduce this self-distillation with born again neural network. So in step 0, we have the model initialized from scratch, and given the input, we have a label. We use the label to train the model, right? We don't train it all the way to converge. But the second step is we try to feed it with the input to the model, and then we get a first generation of student. It's T for teacher, S for student, and the student takes the feedback, the supervision, not only from the output label, but also from the previous generation, the output of the previous generation, using its father as the supervisor of itself. And the third part, we can repeat this process, right? Like the grandparent is supervising the parent is supervising the kid. You can repeat this across many generations. So you only have one model, but it has this kind of iterative training stages, and using both the classification objective and also the distillation objective in the subsequent stages, where the network architecture just have one architecture, and the accuracy keep increasing. And to boost the final performance, since they're of the same architecture, we can directly ensemble them together. And we can have different stages, the result, the architecture from different stage, merge them together to ensemble them. And you have no runtime overhead, since you can directly add those weights. You can also have a weighted average, since the later stage one may have a higher quality than the earlier models. So that's the self-distillation. There's also the online distillation. So what it's saying is that we have the teacher doesn't have to be larger than the student, or the student has to be smaller than the teacher. They can be of the same size. So they are learned together, and we call it deep mutual learning. Previously, the teacher learns first. You first train a pretty big model, and then you fix that model to train the smaller student model. But in this case, both the teacher and student, you cannot distinguish which is teacher, which is student, because they are both initialized from scratch and start the training all together. This is more like your buddy or classmate or deskmate sitting next to you, learning from each other, and also learning from the classification of the final labels. So that's why here, the loss for the teacher and the student both have two terms. One term is the normal cross entropy loss. Given the input, this is student's prediction, this is teacher's prediction. Y is the label. That's the normal classification's cross entropy loss. And also the KL divergence between the student's prediction and teacher's prediction. Similarly, for the teacher's prediction and the student's prediction, we find the KL divergence. You can do that not only on the final output, but also the intermediate feature maps covered in the section in where to match. So here it's not necessarily to pre-train the teacher and the student. They can both get initialized from scratch. And we can allow the teacher to be the same architecture, same size, same capacity as the student.
What's the intuition for why this might be better than just using the same total amount of compute on a slightly bigger model? On a single model?
You don't want a big model, right? All we want is a small model, and try to add some extra supervision so that we can do better than training this small model from scratch. So now you get some extra supervision not only from this cross entropy loss, since these two models might be initialized, although they are both randomly initialized, one may have a better initialization, the other may have a worse initialization. And such randomness matters when you come to the second term, adding the KL divergence, so that it can get some extra supervision and a little bit larger capacity. And also prevented from getting a bad initialization, since now you have two models and two initializations. So here we can see different data sets, CIFAR 10, CIFAR 100. This is net 1 and net 2. Actually, they can be of the same architecture or different architecture for MobileNet versus ResNet. So if we train them independently, it's 93, 92. But if we use this kind of deep mutual learning, the accuracy is actually higher compared with these models training independently. And this is the difference, the improvement. And we see, at least on CIFAR 10 and CIFAR 100, the difference is all positive, meaning that such deep mutual learning is better than this net 1 and net 2 trained independently. I wish the author has provided more ablation study on ImageNet so that we can make this conclusion more solid on larger data sets. At least at this point, we saw for both scenarios where the two networks are the same versus these two networks are different, and both helps to use this deep mutual learning compared with independent training. And finally, we can combine them together to combine this kind of online distillation and also the self-distillation. Here, this paper is called Be Your Own Teacher, Deep Supervision plus Distillation. So here it has several loss functions. So the most straightforward one is from this output label, okay, supervision from the labels. Also, it has a supervision from distillation. For example, this neural network has 4 blocks, 3 outputs. Certainly, the deeper you go, the higher the quality. So if you can only run the first block and then insert a classification layer, just like is GoogleNet, where you have the early exit, and you can calculate the softmax to get a prediction only after you pass through the first residual block. We can imagine the accuracy is the lowest because you just pass through the first block, but acceleration is pretty good since you don't have to run the remaining modules. Computation, the workload is much smaller, so the acceleration is better. While if you go deeper, the accuracy gets better, while the acceleration gets less significant. Question here?
Like the first day of class, you mentioned this example of you using a lot of these tiny ML like algorithms to handle models manually, and you talk about auto ML and how you're able to scale up these faster. As we're going through these lectures, like, was this also something that you done with the auto ML, or are these kind of like a case-by-case basis where you really need to manually look at each network?
So this how to supervise the training. It can be auto architecture design or the manual architecture design. So teacher and student, this methodology doesn't care if the teacher's architecture or the student's architecture is manually designed or automatically designed. But once you have architecture, this is all about how to improve the accuracy of that architecture. Say you use one small network, automated approach, you find a good architecture. but can I better further improve the accuracy of that one using the teacher-student this kind of supervision. So the student model can be either manually architected or automatically architected.
Yeah, architecture side of it was this process. This is pretty feasible to do this in a more or less autonomous way, or you kind of
Certainly, because the block, you can do it in an autonomous way, because here within this block, like we mentioned, we can figure out what is the channel number, how many stages we have, that part. But here, novelty is these lines, where to insert the loss. Where do we insert the loss? Previously, we only insert the loss in the very end. But now we insert the loss by using the later stages feature map to also supervise these earlier feature maps. No matter, this is orthogonal to the architecture, but this is about how do we supervise, how do we train this model. So if we go through the 4 techniques we visited so far, right? Pruning, quantization, they work on a pre-trained model, you prune and you quantize it. Neural architecture search can invent new model architectures that is small and compact to start with. And also distillation, teacher-student model, teacher-student framework can facilitate the training for all above the scenarios. For example, a natural way is to use a dense network as the teacher and a pruned network as the student, so that you can improve the quality, the accuracy of the student model with of the pruned model with the original dense model. Or you can use this distillation to fine-tune a quantized model, right? The full precision model being the teacher, the low precision model being the student, right? You can also apply this distillation to neural architecture search. You can design a very small architecture, and then while you are training that, you use this distillation approach with the help of a teacher. So that's why we put distillation after pruning, quantization, and also the neural architecture search. And this is orthogonal. We can apply this distillation to all of these kind of 3 techniques. So here we can see, since we can exit early, let's see, for different networks from ResNet, VGG, ResNext, wider ResNext, etc. What is the how deep should we go? So here we have 4 stages, right? We have 4 stages. For ResNet 50, we have to go to classifier 4, stage 4. We have to finish everything. But for VGG 19, only after 2 classifier stages, we can match the accuracy or even better accuracy compared with the baseline. Or ResNet 152, finishing 3 stages, can match or even better accuracy than the baseline model. Okay, so the earlier, the better. Like this one, after classifier 2, it already matches the accuracy as the baseline. So it doesn't have to go through anything deeper. You can certainly go deeper and even ensemble the prediction across different stages together. And you can see you can achieve even better accuracy compared with just running the model, the baseline model. So certainly, this adds some complication to use later stage feature map to supervise the earlier stage, and use a later stage prediction to supervise earlier stage prediction. That's why you get different wires here. We can see accuracy-wise, this CIFAR 100 shows quite consistent performance improvement over the baseline. And the predictions from its intermediate classifiers sometimes even outperform the baseline. All right, so that's all for the self and online distillation. Let's take a break, then talk about different tasks. All right, welcome back. Let's continue our discussion about knowledge distillation, not only for classification tasks, but also for diverse tasks. So knowledge distillation, for example, for object detection tasks. So again, we have teacher and also student, but here we have slightly more stuff to predict. You know, predicting the object detection, we need to predict the bounding box, right? So it's the face, this is a face, which need a regression, the bounding box regression. And also for each bounding box, we need to classify what is the class in each bounding box. So there are two problems. There are a lot of foreground and background, right? So most of the case, this is the background. So we need to balance the foreground and also the background. And secondly, the bounding box is a regression problem. It can be anywhere. It's not a classification problem. How do we deal with that? Something simple is the intermediate features. We can still try to match those features from the teacher and the student by using a one-by-one convolution to match the dimension, to match the shape. But here, which is the classification, the bounding box. What is the class for that bounding box? Here we use a weighted cross-entropy loss. There is a WC over there. Why we need that? Because we want to use different weight for the foreground and also background classes. Maybe the foreground is more important, background is less important to handle this class imbalance problem. Since there might be a lot of rivers or trees, but very few cats and dogs, we want to make sure that it's balanced. And also here, we want to exploit the teacher's prediction until the student is a little bit higher by M, higher accuracy compared with the teacher. So we allow the student to surpass the teacher, but only by a certain margin. And after that, we stop. After that, the loss becomes zero, which means we are no longer learning from the teacher. Otherwise, if the teacher is already weaker than the student, there's no sense to learn from it. Another issue is how do we convert this regression problem into a classification problem? When we are doing detection, we want to have the bounding box for the object, which include 4 real numbers, x1, y1, and also x2, xy, x2, y2. We can turn it into a classification problem by discretize both the x and y dimension. So here we divide the y-axis into 6 bins, and also the x-axis into 6 bins. And we can see which bin the target is located at, and use that as a 1/6 classification problem, so that we can use our initial methods to calculate distillation loss between the two probability distributions among that classification problem by the teacher and the student. So that's for distillation. Another important vision application is the segmentation. Like from the SACV, just happening this week. Best paper honorable mention is the segment anything model. Right? So you want to segment, give a pixel-wise prediction, like this is the cloth, this is the whiteboard, this is the blackboard, to segment all the pixels. And how do we distill on top of it? Again, we can try to match the pairwise, have the pairwise loss for the feature map between the teacher and student. Okay, this is the input, this is the intermediate feature maps. And we have the pixel labeling here We can also have a new thing, which is a discriminator network, try to provide adversarial loss. So here is a score map for the teacher and score map for the student. We try to use the GAN approach to train a discriminator network to make sure that the student is performing so well, so close to the teacher, so that you can try to fool this discriminator. It cannot tell whether the segmentation map, if it is provided by the teacher or provided by the student. We try to make the student so strong to cheat the discriminator and try to train the discriminator to be very strongly to tell whether it's from the teacher or it's from the student. They improve jointly so that in the end, the teacher and student both, the student and also the discriminator both get it pretty strong. And also knowledge distillation for GANs. This is from my students' work called GAN compression. So for GAN, we have this GAN loss, just like we mentioned. The generator try to fool the discriminator, and the discriminator try to distinguish between if it is real or fake. So that's a regular GAN loss. C GAN for conditional GAN. We have the normal distillation loss like before. For the teacher, for the student, different layers. We use the one-by-one convolution, try to do the projection to match the dimension for the intermediate feature map. And here we also have a reconstruction loss. For the paired conditional GAN, we can use the grounded truth to supervise this generated image. For example, turning a horse into a zebra, or horse into a zebra. This is the grounded truth of the zebra. And for the unpaired conditional GAN, we try to use the image generated by the teacher to make it match the image generated by the student. And altogether, the loss is kind of three terms: the regular conditional GAN loss, the reconstruction loss, and also the distillation loss. That is the method we use combined with this one-for-all approach. Actually, that's another example showing we can combine neural architecture search with distillation, because when we are training, we have a candidate generated pool. We can select a full channel or partial channel, similar as the one-for-all approach. It's elastic. You can choose different part, a sub-network rather than the full network. Finally, we can accelerate this like horse to zebra from 56 gigaops to only 3 gigaops, 16 times reduction. And also the frames per second improved from 12 frames per second to 40 frames per second. And the FID, which is the quality, is even better, even lower. Here's another example. Before GAN compression, every edit, the output is very slow. Like we can remove the logo of this shoe. This is called edges to shoes. You draw the edge, comes with the shoe. We want to draw another logo, but the frame rate is pretty low, 1.6 frames per second running on a mobile device. Jensen Nano GPU. We tried many times to make it into a Nike shoe. Change the logo, but it's very slow. Can we make it faster? Now we see on the right-hand side, the frame rate increased to almost 4 frames per second. So you can erase and draw new stuff relatively more quickly. And as you draw the logo on the left, continue to view the output on the right. It looks better, faster. for interactive photo editing on the mobile. We can also use knowledge distillation for natural language processing tasks to transfer the attention map. So this is the transformer architecture we discussed, has multi-head attention followed by the FFN layer, feed-forward layer, which is basically FC layers. And then we have QKD projection and also output projection. We have the normalization layer. In this figure is showing this post-norm, but sometimes in recent large language models, people are doing pre-norm to have the normalization before this multi-head attention. But here, what we are trying to match is attention map. What is the attention map? So this is the teacher, the attention map. And this is a student with attention transfer versus student without attention transfer. With attention transfer, we can see teacher and students attention map becomes much more similar than without this kind of transfer. And here versus here, we can tell this is getting closer. Which again trying to match the relationship between different tokens, try to match this attention map. And also we can map the feature map, try to match the feature map. So no matter what kind of architecture, what kind of task it is, the key is try to find what to match. And finally, let's talk about network augmentation. We have heard of data augmentation. What is network augmentation? So the key idea is the model is just so small. How can we augment the capacity without having to increase the runtime at inference time? So to learn about network augmentation, let's first see data augmentation. So data augmentation deal with overfitting, but network augmentation deal with underfitting. So if the model is pretty big, but we don't have enough data, we can do a data augmentation. Try to cut out a certain region, or mix up and dot, or auto augment the tint, the color, to do rotation, to do crop, and do automatic combination of them. And drop out is another concept, right? To prevent overfitting. At training time, we can randomly remove different activations, but at the inference time, they all come back. And you still run the full model at inference time. Only during training time, you randomly remove some of the neurons. There is also a spatial dropout. You can remove the whole channel, or drop block to remove more coarsely a few blocks. So all these techniques, no matter if it's dropout or data augmentation, can improve the large neural net's performance and prevent overfitting. Like this is Resonate 50 with 4 gigamax. The original accuracy is about 76, a little bit more than 76, top line accuracy on ImageNet. But by applying mix-up, auto-augment, drop block, the accuracy can be boosted to 78, more than 78. Unfortunately, these methods hurt tiny models' performance. Like this is mobile V2 Tiny, which has only 23 millimax. A few orders of magnitude difference from this Resonate 50 with respect to the presentation. The baseline model is more than 52%. It's pretty low, but applying these techniques, mix on auto augment, drop block, the accuracy is even lower, less than 50. So that's the issue, where we don't have a good approach to train these tiny nets. And conventional data augmentation, drop out, these approaches actually doesn't work for tiny neural network training, but even hurt tiny neural network training because they don't have enough capacity. So how do we solve the issue and improve the capacity of tiny models. We can augment it with the help of neighbors. We'll talk about self-distillation, joint learning. You want to learn, you want to have a buddy to learn together with yourself. So here, what we do here is we want some extra supervision during the training. So we build an augmented model, and the target tiny model is a subset, just like the once-for-all network. They share the weights. These red weights are exactly the same as the red weights in the student. And it also has some actual weight that is in black that only belong to the augmented model. So given the input-output, we not only pass the forward and backward to get the loss of the base model, but also from the gradient from this augmented model. The augmented model share the weights in the base tiny model with some extra some augmented model weights. Since they share the weights, all the gradients will also flow to the original model to update those red shared weights. And at each step, we can sample different augmented model, large and small, just like what we did in the once-for-all network. And in this way, we can get some actual supervision by sampling different augmented models. But they all have this core, which is the tiny model in the middle. So for a tiny neural network, the network augmentation can improve both the training accuracy and also the validation accuracy. This is movement V2 tiny improved accuracy by 1.3 and 6%. However, as we expected, it only improved the training accuracy of a large model, but didn't improve the training accuracy, the validation accuracy of large model, because it's preventing the underfitting issue. And the large model already have enough capacity, which doesn't suffer from this issue. So we can actually use network augmentation together with knowledge distillation. So this is the baseline of the V2 knowledge distillation, network augmentation, knowledge distillation plus network augmentation can consistently give good results across movement V2 tiny, movement V2, V3, and proximity NAS. And compared with knowledge distillation, and also just train it for a few longer epochs, since we are afraid of underfitting, how about we just train longer? Actually, we find that train longer doesn't help, sometimes even have a negative effect. So this is a transfer learning task, not only comparing the ImageNet accuracy, but also show the transfer learning capability. And this is the improvement over the baseline. And also on object detection, for the same number of computation max, we can improve the accuracy quite consistently. This is on mobile V2 0.35. One is on Pascal VOC, one is on COCO dataset. Also, for the same accuracy, you can reduce the computing. All right, so in this lecture, we introduce knowledge distillation to use a teacher model to help the design and training of a small student model. We talk about where to match. You can try to match the weight, the activation, the gradient, the sparsity pattern, the output, the intermediate feature maps. And also talk about self-distillation, where you don't necessarily have a teacher, but you can just have just distill yourself during training. For different tasks, detection tasks, segmentation tasks, NLP tasks, and more. And finally, use network augmentation to prevent underfitting for small models. And in the next lecture, we'll introduce a very small network family called MCUNet, which is applying what the lessons we have learned so far to design, to have algorithm assisted co-design for tiny ML, which can be deployed microcontrollers. That's all for today's lecture. We'll see you next week. And for those who haven't signed on Piazza, it's good timing to log into Piazza and join our discussion group. And TAs will answer the questions over there.